Hello, my name is Tyler Ingle, and today I'll be presenting our statistical evaluation of aluminum part strength. Our goal with this project was to determine whether the aluminum components being produced meet the required mechanical performance standards and whether the manufacturing process is consistent, reliable, and capable of maintaining quality over time. This project focused on three main objectives. First, we evaluated the strength of aluminum components to ensure they met required specifications. Second, we looked at the process consistency, whether the manufacturing process remains stable and produces parts with predictable mechanical behavior. Finally, we aimed to detect any early indications of quality issues. Identifying problems early helps prevent defects, reduce costs, and improve reliability in production. To conduct a meaningful analysis, we used a representative sampling strategy. Parts were selected from several production batches so we could capture natural variation in materials, machining, and heat treatment. Each sample's ID, batch number, and production conditions were recorded for traceability. For tensile testing, we followed standardized procedures using calibrated testing equipment. Preparation, setup, and testing parameters were kept consistent to reduce variability caused by the testing method rather than the material itself. All test conditions and measurements were documented to ensure accuracy and repeatability. Here we present the statistical results from testing. We summarize the mean strength values, standard deviations, and sample sizes for each group. To determine whether differences between batches were meaningful, we used hypothesis tests and reported the p-values associated with those comparisons. We also calculated 95% confidence intervals to give a statistical range where the true mean strength is likely to fall. Finally, visualizations such as histograms, box plots, and scatter plots help show how the data is distributed and highlighted trends or unusual variation. Based on the statistical findings, we can begin making engineering decisions. If strength values fall close to the lower specification limits or show high variability, additional testing or design changes may be recommended. If results show consistent performance and acceptable safety margins, then the current process can be considered stable. These results also help assess overall reliability and identify any potential failure risks. Understanding where deviations occur allows us to adjust manufacturing or quality control strategies before major issues develop. In conclusion, the statistical evaluation helps confirm whether the aluminum parts meet mechanical performance requirements and whether differences in strength are statistically significant or simply due to normal variation. The mechanical safety assessment ensures that the tested components satisfy operational loads and do not pose a failure risk. Lastly, the analysis supports quality assurance by verifying compliance with specifications and ensuring consistency across production batches.